So in this problem, the first thing that we have to do is calculate the equivalent capacitance of all of these capacitors. So how do we do that? The first thing we notice is that the three C1s in the end are definitely in series, right? We can't really say anything about the other capacitors. They're neither series nor parallel, but the three C1s in the end are definitely in series. So we know how to combine capacitors in series. So let us do that. And let's just combine the last three C1s into one equivalent capacitance. All right, so C1, C2, C1, and then C1, C2, C1 again. And then what we've done is we've combined the last three capacitors into one C equivalent there. All right. Now we know what the C1s are and what the C2s are. C1 is 6.9 microfarads and C2 is 4.6 microfarads. Let me just double check that. 6.9, 4.6. All right. Oops, 4.6, not 4.2. All right. So, okay. So now let's call this as diagram 1. Let's go ahead and simplify this a little bit more. Actually, we can find the first C equivalent. It's going to be 1 over C1 plus 1 over C2, 1 over C1 plus 1 over C1 plus 1 over C1. And that's our 1 over C equivalent. You can kind of see that this is 3 over C1. And so C equivalent is going to be C1 divided by 3. So that's going to be 2.3 microfarads. And just to reduce the clutter, I'll get rid of this. And this is going to be 2.3 microfarads. All right, so now let's simplify one more step. So we've got C1, and we've got C2, and we've got C1 again. Then we've got C1, we've got C2. Notice that the last C2 and our C equivalent are in parallel, which means that they can be combined using the rule for equivalent capacitance for capacitors in parallel, which is you just add them if they're in parallel. So let me just pull up a calculator. So we have to do 4.6 plus 2.3, 0.6 plus 2.3, that gives me 6.9 again. All right, so 6.9. And then we have the C1 again. All right. So that's diagram 2. So we've combined the C2 and the C equivalent of diagram 1 to get to diagram 2. All right, now diagram 2 can also be simplified one step further, because the C1 and the C equivalent and the C1 are in series. So we can combine them. So we are going to do 1 over 6.9 plus 1 over 6.9. Oh, they're all 6.9. So 1 over 6.9 plus 1 over 6.9 plus 1 over 6.9 is just going to be again 2.3. So I mean the inverse of that will be 2.3. So this just becomes C1 and then C2, C1 again. And then we're combining the C1, C equivalent, and C1. And once again, we get a 2.3. All right. And so now we need to once again combine the C2 and the C equivalent. So we'll again end up adding 4.6 and 2.3, which once again gives us 6.9. And so we end up with a C1, a C equivalent, which is 6.9, and a C1. All right, so let this be our diagram 3, this is our diagram 4, and then finally we can simplify diagram 4 to make the circuit as simple as it will get. So 3 C1s connected in, 3 6.9s connected in series. So that's a 2.3, as we've seen before. C equivalent equals 2.3. So this is diagram 5, and this is the simplest we can make the circuit, right? We are told that the potential difference V is 420. V is 420 volt. I think that's what it is. Yeah, V is 420 volts. All right. We've already solved the first part. It's 2.3. So this is the answer of the first part. All right. Okay. Now this to do the second and the third parts, what we need to do is we need to unpack the circuit. So we've packed it and made it really compact, and now we just need to unpack it, and that's what we need to do. So part B is asking for the charge on the 3 capacitors nearest A and B. So we need to find the charge on this C1, this C2, and this C1. All right, so let's go ahead and do that. So we have the charge 420 volt on across points A and B, and the capacitor C equivalent is between them. So we can find the charge on this C equivalent. So let's do that. So that charge is going to be Q is equal to CV, right? So V is equal to Q divided by C. So we're going to, Q is equal to CV, that's what we need. So we're going to do 420 volts, that's the V, multiplied by the C, which is 2.3 microfarads. So 2.3, 3 times 10 to the power of 6. Oh, I mean 10 to the power of minus 6, sorry. So that comes to 0.00096, if I did that correctly. Okay, so that's the Q, right? So now let's unpack from diagram 5 back to diagram 4. So we know that the same Q will, so in diagram 4, C1, C equivalent, and C1 are in series. So they must all have the same charge that we just calculated as the charge 0.00096 coulombs. Actually, what we could do is, instead of working with coulombs, we can probably work in microcoulombs. If you just do 420 times 2.3, you get 966 microcoulombs. So that might be a little bit easier. So 966 microcoulombs, I mean. All right. So the same charge, 966 microcoulombs, is going to be on C1, C equivalent, and C1 in diagram 4, because they're all in series. So we're looking at diagram 4 now. All of these will have the same charge. All right. Okay. And I'm writing the charge as a Q, but it's really a plus Q and a minus Q on each plate. Okay. So the question was asking, find the charge on the 3 capacitors nearest A. So we've already found the charge on the 2 C1s, but we don't know what the charge on C2 is. And we did get the correct answer. 966 microcoulombs is what we got, and so I have it rounded up over here. All right, so now we need to find out what is the charge on the C2 that is connected to the first 2 C1s, right? So for that, since we fully worked out diagram 4, we have everything. Now we need to excuse me, now we need to step to diagram 3. But before we do that, let's also find out the potential differences. So what is the potential difference across C1 in diagram 4? So what is this potential difference? V is equal to Q over C, right? So the potential difference across that C1 is going to be Q divided by C. So that's going to be 966 microcoulombs divided by 2.3 microfarad. So 966 divided by 2.3 is 420. Did I do that correctly? So no, it's so C1, sorry, C1 is 6.9. Sorry, it's not 960, not 2.3, 6.9 microfarad. And so 966 divided by 6.9 is 140. So there's 140 volts over here. And since they're all they all have the same capacitance, they'll all have the same voltage. So 140, this will also be 140, and this will also be 140. And you can see that the three 140s add up to 420. All right. So we found the potential difference across all the capacitors in diagram 4. That means we have fully solved diagram 4. We have the capacitance, potential differences, and charges of all the capacitors in diagram 4. Now let's move over to diagram 3. So in diagram 3, we have, instead of C equivalent from diagram 4, now we are back to C2 and the other C equivalent. So these two, the C2 and the C equivalent in diagram 3, must have the same potential difference as the C equivalent in diagram 4. In other words, the potential difference across C2 over here, as well as across C equivalent, is 140 volts. Where should I write that? 140 volts. So both C2 and C equivalent have a potential difference of 140 volts. That's it's not very clear, so let me just write it over here. So this potential difference is 140 volts, as is this potential difference. They're both 140 volts. Okay, so now knowing that the potential difference across the C2 is 140 volts, we can find out how much charge there is on C2. So C2 was 460, now I can't read my handwriting, 4.6 microfarads. So C2 was 4.6 microfarads, and it has a potential difference of 140 volts. So Q is equal to CV. So that's 4.6 microfarads multiplied by 140 volts. What is that? 4.6 times 140 is 644 microcoulombs. So that is the charge across this C2. That's 644 microcoulombs. Yeah, I got that correct too. Okay. All right. So we have the charge across C2, and we have the potential difference across C2 as well. That's 140 volts we figured out earlier. Okay, so now the next thing we need to do is, so we figured out everything over here. We now need to find the potential difference across CD. Okay. All right. Okay, so in order to do that, we need to go back to from diagram 3, we need to go into diagram 2. So in diagram 2, the C equivalent of diagram 3 gets replaced by a C1 and another C equivalent and a C1, right? And since the C equivalent of diagram 3 has a potential difference of 140 volts, that potential difference is shared by the three C1s. And so there, I mean, the three 6.9 microfarad capacitors. So C1, C equivalent, and the other C1, they're all 6.9 microfarads. And so we've seen that they're going to share the voltage among themselves equally because they have the same capacitance. So that means each one of them will have a potential difference of 140 divided by 3. And so 140 divided by 3 is what? 140 divided by 3 comes to 46.6, so 47 volts approximately. So each of these will have 46.6 volts, and then this one will also be 46.6, and this one will also be 46.6. And that really answers the question. It's asking for the potential difference between these 2 points, and so it's just going to be 46.6. And that is the answer. Okay. And so that's how you would, that's how you can first pack the circuit into the most compact form, which is diagram 5, and then gradually unpack it in steps. All right.